Hi there. Okay. Um, so right now I'm going to be giving you a little bit of an overview on reverse engineering some aspects of it. Now I do have Windows and Ubuntu fired up here just for some quick recaps. I could go a lot more in depth, but I just want to make a very quick overview on how to use Ghidra on Linux, on Windows, sorry, and then we can jump into Ubuntu to try some stuff out in other areas. Now this should be Windows. Let's go to properties and change this. Yeah, this is Windows. This is Windows. Okay. So this is Windows. Just prepared a build of Ghidra, which I'm going to execute right now. And we're using this tired flag right here, the capture the flag thing. Challenge 12. And that's what I'm going to use. So I'm going to create a new project called tired, or I guess, and I'm going to import this file to import. Now, the most important thing is to just understand what's happening. Now, I'm just going to make a very quick overview and examples on how to do certain things, how to interpret what's happening, really quick. But this is something that would take hours and hours and hours to explain everything in depth, and I can do that. I'm planning on doing that at some point, but I can do some parts of it if that needs to be done as well. If people ask me to do that, but okay. So let's open up this in Ghidra. Okay. Now Ghidra asks if you want to analyze it. You can analyze it. It will appear here in terms of the decompiler, some useful code that kind of gives you an idea of what the program is working. Now, what is contained inside the program is actual code. Okay. Every file contains binary data inside of it. Well, not necessarily every executable file would contain binary data inside of it. And I don't want to generalize because you might create some form of executable file that will be executable in some operating system that you create. That will not be executable, but it doesn't. That will not contain binary. But let's just assume for this particular case, again, I'm going to be oversimplifying a lot of stuff. So let's assume that all executable files will have binary data inside of it, and this is how it looks. This is the hexadecimal representation, right? Hexadecimal representation. These are the hex numbers. This is the assembly code, right? This not very well visible, but. And these are the memory address locations. And it starts with 804,000, whatever this number is, and it goes down up. It goes down to it increments until the end, right? From this memory location to the rest. Now there's this is the prefix that you would add as it goes into memory. These are like the lines that are really there. It doesn't matter for right now. But a very interesting thing that you see right off the bat is this, the initial, right? And you see a little ELF here. Well, this is an ELF file, right? It's the ELF format, which is executable and linkable file. And it's defined by its magic number right here as the 7F454C46. This is what tells you already that it's an ELF. 45C46 obviously is ELF in ASCII. The 7F is just the prefix of the ELF file. And then you have other bits that are part of the ELF header, right? You know that this is a 32-bit file because because this bit is 1. Oh my god, I forgot what I was going to say. Oh, and the rest are just other properties as well of the elf file, and this belongs to the elf header, right? And the whole header is basically a collection of properties of the file itself. So it's not very important right now, but it defines the entry point, it defines the size of the header of the program as well, because the programs have headers too, which you can see here as well. And this was compiled using GCC, most likely, and because you can see loads of artifacts here, etc. And then in the dynamic, oh my god, I can't remember words right now. You get what I mean. It's not very important at this moment anyway. Now, what is important is this tab here, where you see your imports. You can see the external imports that are done from that are automatically put up in here. You don't actually write this, but it's put up in here automatically when you use GCC, because it will start using all the libraries and stuff, and it's going to import it. The libc obviously. You have exports, and then you have the functions. These are all the functions that you have. Loads of functions you don't code yourself when you use GCC. It just gets added into it. But then you have the main function. This main function is your actual main function. And if you go right here, you see what the main function is doing. This is where the function starts. And yeah, you're defining the entry point of the program, blah, blah. Anyway, this is the main function, the actual hexadecimal code for the main function. Now, assembly, LEA and push, mov, these are instructions that do something, right, with whatever's here. It's assembly. But all these instructions translate directly into hex code, which translates directly into binary. And this is what is inside of your file. This is just a representation for understanding and, for you to be able to code. Because, writing push EBP is more intuitive than writing 55, right? Now, how do you know the opcodes and what its instruction does? Well, I prepared some links for you. I prepared these links. I already opened this up. This is the actual Intel manual of software instruction set reference, whatever. It contains all of the instructions with all of the references, with all of the opcodes available, with instructions, with descriptions, loads of this stuff. Then I also prepared another one, which is essentially just a little compact version, because this has 2,000 pages. Compact version that you can just look up the one you want, click on it, and it will give you some descriptions of it. And this is just a quick Wikipedia page if you need even less information. If you just want to, you don't remember what I don't know what the damn it I can't maybe you don't remember what the LES is, right? No, that's stupid. Everyone would remember that. You know what I mean? Maybe you don't remember like something like what the IMUL is. Like if it's the IMUL or the mole that is the sign multiplication, and you can just come up here and see, oh, it's sign multiplied. These are opcodes, blah blah. But it's very limited information. For more information, you got these. For even more information, you got these. And this is how you see kind of what is what, right? Now, a very important aspect to understand is also the stack of the program. So programs think that they are the only entity in the computer using the memory, right? They basically think that the memory that they have access to is all the memory that exists, and they're the only programs that have access to it. Obviously, that's not the case, but that's, in the program's mind, they're using all of the memory available. And this simplifies the organization of the structure, of the memory structure. And what you'll end up having is, oh wow, this actually separates this very well. We're not going to get into this. But essentially what you'll have is you'll have high memory on top, low memory on the bottom. So think of high memory as a bigger memory address, right? So low memory, let's say, starts at 0, and high memory, let's say, stops at FFFF, whatever, right? This is not really when it stops and when it starts, because there are limits. You can't start at 0 and end in F. But for simplicity, let's say that high memory would be the biggest number, low memory would be the smallest number, right? So let's imagine, you know what, let's do this. It's just easier to do it this way. And this is something that you'll see. I can even show you on Ubuntu right after, or at some time, at some point. But it's something that you'll see, and it's really important to understand this. So let's say that this is this right here would be the stack, right? Let's say that this right here, let's say, would be the heap. You know, we'll have a lot of like the unallocated memory around there. And then we're going to have the other sections, right? So we have the program sections, and we have the executable sections of the program. This is not really important for us that much, you know, but this would be the BSS section. We have the text section, we have the data section, or the other way, but it doesn't matter. For us, we don't care about this right now. We only care about the stack right now. Okay, if we talk about the stack itself, it's a very simple thing. It's basically a stack where you will be putting stuff inside of it, right? So you put stuff inside of the stack. Let's say you get a function, and in the function you declare a equals 1. Well, guess what? The stack will have 1 right there. If you declare b equals 2 after that, it will be put b equals 2 again. This is high memory, this is low memory. Stack grows from high memory to low memory, right? So it doesn't start with 0 up to high memory. It starts from high memory to down. So this is the bottom of the stack right here, bottom of the stack. This is the top of the stack. The top of the stack has a register called ESP or RSP, depending on architecture, if it's 32-bit or 64-bit, or even 16-bit, would only be SP. Doesn't matter, but this always points to the top of the stack. Now we have 2 instructions. We have the push instruction right here, push instruction, and we have the pop instruction somewhere here. Now, the push instruction pushes something into the stack. The stack is a last in, first out. So the last one that goes in is the first one that goes out, right? So one goes here, then one goes there, then one goes there. So if you push something else. See, you push something else, you push something else. Now the pop, when you pop, is when you remove it. When you remove it from the top. So you remove this one first, you remove that, you remove that, you remove that. Right? That's how it works, essentially. And the stack serves to store local variables and function arguments when you need it, and then destroy them when you don't need it anymore. That's the little basic idea of registers, of the stack. And the registers that we have many kinds of registers. We're just going to look at some of the general purpose registers, which are EAX, EBX, EDX, ECX, ESP. And these are 32-bit registers. The 64-bit versions are, instead of E, would be R. So RDX, RAX, RCX, etc. Now the ESP is very important. It's the stack pointer. Again, points to the top of the stack all the time. So, again, in our little example, if we add something to the stack, let's say we add A, the ESP is pointing here. But then we add B, the ESP is now pointing here, because it always points to the top of the stack. Now we pop B disappears, ESP is pointing towards A again, right? That's all the ESP does. And the other registers can be used as, most of the other registers can be used in any way you want. They have standard definitions for them. You can look them up. It's not a very big deal. They're just let's say that they are permanent variables that we can dump stuff inside and retrieve it and make operations with it, and we should. Now, those are registers. That's the stack. So it makes sense that you push things into the stack first. So this is why, for example, right here, when we're defining local line 59 equals blah, blah, blah. This is a moving of this. But remember that before that, where was it? Before all this, we did something. We had to do that. We pushed EBP, right? And as we pushed EBP, now we can use EBP to do things. Now, actually, we usually push EBP to move ESP to EBP because it's a lazy way to keep track of where we are before. So we do that all the time. So for example, when you get a call, just before of a call function, you will see things like this happening. Because it's just a very lazy way to keep track of where you were before. It's not very important. And it's not necessarily used that much. But whatever. Anyway, the EBP was pushed, and it was and the value of ESP was moved to EBP, and now we can make these operations. Because again, remember the ESP points to the top of the stack, right? And the EBP now is the same value of the ESP. So whatever the local 59 variable is, it's the offset where this is, right? This is the offset to EBP, which is the top of the stack, right? So we're just going from the top, and we're going to access the variable in reference of the of EBP here. Not a very important thing, but that's it. That's what we're doing. So instructions: we got the push, pushes things into the stack. We got the pop, removes things from the stack. We got LEA, just loads the effective address of this. Not incredibly important for now to understand it. We have the move. This moves. This is the destination. This is the source. So move EBP ESP moves ESP into EBP, right? Not the other way around. So this moves into that. The right moves into the left. Subtract again. This one is the destination. The left is destination. Right is the target or the source. So this is going to subtract ESP by 0.50, right? So this is going to get subtracted from this. Call is essentially like a jump to a function, but it's basically it's jumping to the address of the function, and then it's jumping back when it returns. So it executes this function wherever this is in memory, and then it just comes back to it and it continues. Add, again, it just adds, and again, this is always the destination, so adds this into here. EBX holds the addition. ESP, the subtraction, we covered that. So subtraction, blah, 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 and then add. And then we have very important things. We have compare, we have J and Z. Compare compares two values, 0x22 with EAX in this case. The compare, what it really does, it subtracts EAX by this, essentially, and it sets the flag. So if EAX minus 0x22 was 0, it sets it sets the 0 flag, and because it sets the 0 flag, the JNZ can work. And what is the JNZ? The JNZ is a conditional jump. It's a jump if not 0. What is not 0? Well, if the flag is not 0. Now, there are flags that exist. I'm not going to go too deep into that. Let's just think about it. If a result of some instructions, for example, to compare, if the in arithmetic instructions, if the result of those are 0, there is a flag that gets activated. So the bit of that flag becomes 1, and that flag is the 0 flag, right? There's another flag for other things. There's a carry flag if there's blah, blah, it doesn't really matter right now, but and also I'm explaining this in a very simplistic way. The flag is they're not really multiple flags in a way. It's one value, but each flag essentially is a mask of that value for a specific bit. The whole thing is a huge is a huge value, but it doesn't matter. Just think about it in this way: if a result of an operation is 0, oops, the flag gets set, the 0 flag, and the jump if not 0 will jump if the 0 flag is not set. So this is why when you come up here to your code, you see if s var equals this, do that. Else, try again. Now, if s var equals 22, what this means is the same thing that we're doing here. Now, this is the compare EAX to 0.22. So what does this do? This removes 0.22 from EAX, so it subtracts. And of course, if EAX is 0x22 and we subtract this, it will be 0, right? And the 0 flag will be set. So if the 0 flag is set, this will not jump, because this jumps if not 0. So if this will not jump, it will just continue. And if we continue, we see that we are continuing throughout this code right here inside of this, right? Inside of this, and then we're going to the string compare, right? We're executing the code inside of this if. Now, if this is not 0x22, this subtraction will not be 0, so the 0 flag will not be activated, so this will jump if not 0. And we'll jump up to here. And again, this will jump into the function that will put try again into the screen, right? This is the first thing that we can do. That we can identify, right? We can identify things like that based on here. And it's important because knowing the assembly and kind of figuring out what's happening is important, because that's, you know, what you have to do to go on with. And the most important things that you should look for at this level are jumps. If you see a jump if something, a conditional jump, so J and Z, you know, there's a whole list of them right here. Right here, this list, the conditional jump if condition is met, right? GA, GAE, GB, GBE, GC, JC, JCXZ, JE, CXZ, JR, CXZ, blah, 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 right? Loads of different functions. Now, and which would its corresponding opcode. And these instructions are very important because, you know, your program is built on conditions, and those, you know, if you have a program that requires a special key or a special code, now there's obviously going to be a condition, like if the code is correct, if the password is correct, do something, right? Of course, complex programs will have a much more complex way of doing this. It's not just going to be a jump, oh, if string equals that, you know. But if it was, you could patch it really easily. Now, how can we patch this? Well, let's understand what the code is doing first. So we already know that the length, because this calls string length and it's jumps if it's not 0. So we know that the length has to be 0x22. Otherwise, it will jump into try again. If it doesn't, this will happen. What is this? Well, first, he's just setting up a bunch of variables with hard-coded values, right? And then he is going into a string compare. So we're saying compare two strings. And then if the string is 0, and remember, the string compare will return to EAX. We push EAX, we call string compare. The string compare will return to EAX. The return value will be into EAX, and then we will test EAX with itself. And we'll see if the result is 0 or it's not, because if the result is 0, we continue the loop. If it's not 0, we jump back over to try again, right? This is what we see here. If IVAR is equals 0, this equals 0, blah, 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 else try again, right? That's all that's happening. Now, if it is 0, which is what we want, we continue here. And what does this do? Well, you see a jump here. This is not a conditional jump. This will always jump. And it's jumping to this location, where it will already compare something. And it will compare 0x21 with local 14. Because, why? Well, we'll see. Because if it's less or equal, well, it will go into this code that we jumped from. And we'll continue this whole code, and then it will compare again. And then is it less or equal? And boom, right? This is really nice, because this is the definition of a while loop, right? You see here, while this is less than 0x22, do something, right? And it's always comparing to 0x21 to see if it's less or equal, and then it's just going through a loop until it is, and then it continues. And when it continues, it will output the flag. So all that we need at this point is to get into here. How do we get into here? By bypassing this jump that jumps away from here into the try again, and bypassing the other jump, which also goes into the try again. So we just need to change these two jumps. How do we do that? Well, we right-click and patch the instruction. And jump if not 0. What if I do jump if 0? Right? jump F0. Yeah, jump F0. Notice how this changed here. Now, instead of when it equals 22, does the stuff? No, it's the opposite. Else does this. So now you don't have to, I mean, this is an easy thing. You could see it very easily, like type something with length 0x22, but you don't have to because you just patched it. Now, let's go on to the next patch inside of here. What is that? Well, let's go back to the main program, and we already patched the where was it? Where are we even? Here, where is this? Oh, there we go. So we comparing it to 22. We're jumping F0 to try again, so it's not going to be 0 because this will not be true because you don't have to put something that is 0x22 in length. Now this happens, you don't need to change any of this, but there's another jump here, and this jump will lead you right into the try again area. But if you bypass this jump, you don't have any other jumps with conditions to think about. This is a while loop. This is a jump, an unconditional jump. It has to exist because it's the while loop. This inside it, this here is what executes the loop. This is the condition for going back to the loop or not, right? So this jump needs to exist. This is the loop. There are no more jumps until you get the printf flag, and there we go. So this is the last thing that you need to patch, and you can just do this exact same thing. What if we just do jump F0? There we go. Now you see how this changed. If equals 0, it tries again, but if it's not, it does the whole thing again. And now you can save it, and you can export program into binary, and you can send it to desktop as a tired.bin, and you output the file. And there we go. We patched all of the things that we needed to patch, and we saved the file, we exported the file. Now all we need to do is test the file, right? So to test the file, let's move into our Ubuntu. Okay, I'm in my Ubuntu right now. So let's execute tire.bin. Ooh, ouch. Okay. Now here's the thing. Yeah, of course. This is the problem. This is not very well done. Okay. I don't want to fix this. I don't want to fix the specific things. What I'm going to do is I'm going to go ahead and fetch from my computer. I'm going to go ahead and fetch the original one, which I'm going to replace, and I'm going to just make sure that it works normally. And what I'm going to do right now is I'm going to manually change this. So we can see it starts with the elf, with the elf definition, with the header. Now we should see okay. Again, this blah blah. Okay, so right here, if we had a 85 here, right? Oh my god. Okay, wait. I need to do that again because I messed up. And it's important if we had an 85 there, so it's here. this would be the jump that we don't want, right? And this would have a try again. But this outputs the flag. Now let's do the same thing and paste this in, except we remove one of these numbers. Boom, try again. But if we do that, it outputs the flag because this is 0x22 characters in length. Because that jump that we patched was the jump if this one right here, remember? This one right here, 0f85. Right? This was the jump. Let me see if I can put it up still here for you. Where's Streamlabs? Streamlabs. Okay, I don't know. I closed it already. This sucks. Okay, it doesn't matter. It's not important. But it's not really important. It's not very important. But you can see right here, so this is the jump, but you can see right here, 83 F8 22, like this is comparing with 20 EAX with 22, C4, and we get the operation as well, the ESP being added by 10, right? Because oh my god, I lost it. Because here, 83 C4 10. This is the whole part where we compared the EX with 22, and then we jump. And when we change that, of course, you don't jump anymore, right? So now you don't jump anymore. So it doesn't have to be 34. But if it is 34, it will not work, right? Because remember, we switched it. So that's the main idea of this thing. And as I was saying before, you can this is the representation in ASCII, right? And of course, this is representation in hex. But you can represent this in binary, right? This is the actual binary of the code. This is what's happening. Ignore this here, but because this is a little ASCII representations, but this is the actual binary that is inside of the file. Of course, this is super long. No one actually will look at this and be like, oh yeah, that is the jump instruction and what, and just like it's not going to happen. Obviously. Oops, that does not work the way I thought it did. Like, no one actually does that. But editing in hex, yes, this is very important. This kind of hex editing is very important. For example, I'm going to give you a little example here. When you're trying to create code that is substantially small, for example, let's do a very, oh my god, a very simple and hello world program returning 0. Do that. Right, now let's use GCC. Let's make it 32 bits and let's output it as hello. And we got, of course, the warnings because I didn't write it correctly, but it still works, right? It still works. Hello world. There's an implicit import. It's not important, but And of course, if you see this, if you see it's 7,220 bytes long, right? So it's 7.2 kilobytes. We can make it directly in hex if you want to. Well, we know already what we need to start with, right? So we need to start with 7545 for C for 6. You know, the alpha definition 0.1 for a 32-bit executable. 0, 0, 0, 0, 0, 1, 2, 3, 4, 1, 2, 3, 4. This is the classical, you know, not a big deal. Now 0, 2, 0, 0, 0, 3, 0, 0, 1B, 0, 0, 0, 0, 5. We want to make it 4 bytes at the start of the program. So this is the entry point. B9, BD, 80, 85. We need to return. System call. Hello world. 0 at the end, of course, for the little dash, for the little slash n. And then we convert this back to, oh shit, oops, no, it's not what I wanted to do, I messed up. Okay, I messed up. Let's try again. Oops, wait. It's hard because I'm not visualizing it. So for 61, that's 32-bit. Now 1, 2, 3, 1, 2, 3, 4, 1, 2, 3, 4. Probably was right. B, setting the entry point. We're pushing things into EAX, then we're doing system call. That's the way that it works. And I am assassinating elf structure here, but I want to be fast here. I don't want to. Dash n. What the hell? Oh, it's XDD, it's not XSD. I'm so stupid. Okay. There you go. And now we can save this, and now we can try to run this. There we go. Hello world. Now, if we compare this, right, so this is 7,000 bytes, this is a 61. There's a whole difference.